I'm sorry because the title is a bit misleading. So first of all, thanks for the organizers. They've done a great job, and I'm really looking forward to all the talks. And secondly, I hope everyone's healthy and well, wherever in the world you are. Thank you very much for coming to this talk. So it's a little bit misleading. I'm not going to talk about Hopf algebras in the category of SupLat. I'm going to tell you why we should think about Hopf algebras in the category of SupLat. And that's going to be a very categorical journey. But first, I want to tell you some motivation and a very concrete problem that I want to solve, and then I end up in SupLat because I want to solve this problem. So the Yang-Baxter equation appeared in statistical mechanics in the 60s, and really today we're not really going to think about the Yang-Baxter equation itself. We're going to think about the Braid equation, which is equivalent to that. You just put a permutation on top of your solution, and you get the Braid equation. So whenever you had one of the linear ones of these solutions, and I'm going to talk a bit more about that later, they had a deep connection with co-quasi-triangular and quasi-triangular bialgebras. What happened is whenever you had one of these objects on the right, in the end, they're algebras or monoids in the category of vector spaces, and you look at the modules of these guys, and from the representation theory, you get solutions of the Yang-Baxter equation, namely because you're getting a braided category. On the other direction, you have this FRT construction, which you put in this linear YBE solution, and the FRT construction gives you back one of these co-quasi-triangular bialgebras. Now, Drinfeld in '93, I want to say, but I might be very imprecise, suggested let's look at set theoretical YBE solutions. So we want to this is a much easier problem. This should be combinatorial, and let's try to classify finite set theoretical YBE solutions. In the past 10, I want to say 5 years, really, skew brace-wise, there's these structures that have come up called skew braces, that it's a set with two group structures with some ridiculous compatibility condition between them. And people are using these to study set theoretical solutions. And the reason is, whenever you take a set theoretical solution, you can create a universal group, and that guy's going to be a skew brace. And any skew brace automatically has a solution, but really there's another result that tells you if I give you a solution, give you a skew brace, you can generate a bunch of solutions from it. So this picture starts very much looking like the one in the 80s. And the question for me as a guy who's into monoidal categories is, can you view skew braces as Hopf algebras or bialgebras in a reasonable category? So this picture should be copied, but in a reasonable category. And what I'm really going to be talking about in this talk, for the first half at least, is this FRT construction and the categorical FRT construction. What I mean, how to do this in any monoidal category. Some background. If at any point I say something that you're not comfortable with, please ask me, but I'm going to try to go relatively fast through this. So I'm going to assume I have a monoidal category. In the opposite direction of Eugenia's talk, where these weak associators and stuff mattered, for me, they're not going to matter at all, because they're not that it's going to be strict, so I'm not going to have the identity morphism, but I'm going to assume all my associators will look like something that sends A and B and C to A and B and C. So they're all going to be trivial in computation. In any monoidal category, I can define what it means to have a braided object. It's going to mean I have an object X, it's going to be a pair of an object X, and a morphism from X tensor X to X tensor X, satisfying the Yang-Baxter equation, or really what I mean is the Braid equation. So if you're not used to it, in monoidal categories, we have this diagrammatic language where you can write your objects in a row without putting the tensor in the middle, and you can write your morphisms in a column going down. And what I'm doing here is precisely I'm denoting my R like the braid, because I know it's going to satisfy the Braid equation. And if you write down the equation, that's precisely what's happening. So if you look at the left-hand side, R happens in the right two components, then R happens in the left two components, and then finally R happens in the right two components. A little note on dualizable objects. In the end, I'm going to end up with symmetric or braided categories. So it's not going to matter left dual or right dual, but I can say an object X has a dual object with a little X hat whenever I have a pair of morphisms. One of them is the smiley face and the other one's the upside down, cup and cap, if you like to call it, that satisfy this sort of bending and straightening axioms. That's the basic preliminaries, I think. Okay, now it's now the upgraded version. I don't want to think about braided objects in the category as just a pair and a morphism, what I can really look at it is a functor. And what is this functor going to be? I'm really picking a strict monoidal functor from a category which I denote by B. And what is this guy? It's the smallest braided category. You can tensor generate a category. It just has its tensor generated by one object and by a single morphism that satisfies the braid equation. So it's the smallest braided category you can have because it's just generated by one object. And any object in this is just the copies of a bunch of this guy. And any morphism is just generated by applying the braid in a certain way. And now this is going to be a 30-second introduction to Tanaka reconstruction. Why do I want to do this? Because in that FRT business, so I'm talking about set theoretical solution, braid objects in the category of set. That's what a set theoretical YB solution is. And I want to reconstruct, and I want to get a Hopf algebra object. What you do is you have these functors, usually people call them fiber functors. So I have a monoidal, nice monoidal functor from a category D into this category C. And under suitable conditions, you're always trying to realize this D as the category of modules or co-modules over something. And for that, I'm going to need it to land in subcategory of dualizable or rigid objects. Whenever it does that, I can construct this object. So if you're not familiar with coends, you're just going to get, these are all, I needed the image of omega to be dualizable to even be able to make this statement. And then I have a diagram in C, and then I'm taking the co-limit of that. So this is just some giant co-limit. What's the point of this object? If I additionally assume that C is braided, or even better, symmetric, which is going to be in my example, then I have a Hopf algebra or Hopf monoid in this base category C. Just a side note, you don't need C to be braided or symmetric, but in that case, you end up with something here. You do something like this, and this is an entry, and you get something called a Hopf monad. So you can do all these things at the level of bimonads and Hopf monads. So in case people aren't, I just assume people wouldn't be familiar with Hopf algebras possibly. So just a 1-minute introduction into Hopf algebras in an arbitrary braided category. I'm going to assume my category is braided or symmetric. And what I have is I have a single object with a monoid structure and a comonoid structure. Going back to that diagrammatic language, if you're into it, I'm really into it, so I have to mention it. You would write down your multiplication, for example, like this, as something going through 2 copies of H to 1 copy of H. This is your units. This is your co-units, and that's your co-multiplication and co-unit. This is associativity, the unit axiom, and then the dual versions of these for the co-multiplication. Now, the additional axiom you need to get a bi-algebra, I'm not going to say bimonoid because bimonoid has a different meaning in the literature for some reason, but a bi-algebra in your category, I'm going to input this extra axiom that I want to hold, and I want to emphasize that here, maybe in a different color, this is the braiding of the category. Yeah, there's no YBE solution here. This is the whole category has a braiding, and that's the braiding of the category. This is equivalent to saying that I want this monoid not to be a monoid in C, but actually be a monoid in the category of comonoids in C. And for that to make sense, I need the category of comonoids in C to be monoidal, and that is really, you need a braiding or a symmetry. And you could really swap the co-monoid and monoid words together. But who cares? We care about this at the level of reconstruction. So what does it mean to really have a bimonoid? Well, because you have a monoid and a comonoid, you can look at the category of comodules or modules over these guys. And whenever you have a bi-algebra, what it's saying is that these categories are going to be monoidal, but not only are they going to be monoidal, they're lifting the monoidal structure of the original category. So bi-algebras under a minute. Now, let's talk. I don't want to go through Hopf algebras because either you know them, and if you don't, there's nothing this technical condition will add to it. So Hopf algebra is just an extra condition. At the level of reconstruction, at the categorical level, what we care about is whenever C has a closed structure, and I'm assuming people are familiar with closed monoidal structures since they're enrichment talks. Whenever you have a closed structure, the Hopf algebra structure allows you to lift that closed structure in addition to the monoidal structure, the category of modules. And it's something necessary when you want to talk about rigid objects, really. So at this level, we really care about rigid objects. A word I used in the first slide was co-quasi-triangular. So a co-quasi-triangular structure is going to be something like it's an existence of a morphism from H tensor H into the monoidal unit, which I didn't really mention, satisfying a bunch of axioms. I think it's lagging a bit in appearing. And all it does, it makes the category of co-modules. That's why there's a co here. It makes it braided. Now, let's go back to the reconstruction paper, reconstruction perspective. All I care about is that if I start with a category that's rigid, if my D is rigid, this guy is not only going to be a bi-algebra, but it's in fact going to be a Hopf algebra. So that's the first thing that it tells me. And whenever this D, which in my case, it's going to be the smallest category of the smallest braid category, whenever it's braided, it equips this guy with a co-quasi-triangular structure. So let's go back to the first slide and the motivation. What happened here is, let me explain what happens in this slide. So really, I want to talk about linear YB solutions on finite dimensional vector spaces. Why? Because I need my fiber functor to land in the subcategory of rigid objects, and rigid objects in VEC are exactly finite dimensional vector spaces. So there was a little bit of a lie in the first slide. And when you apply the machinery that I talked about, you get something called the FRT bialgebra, which was done by Fadil, Rashitikin, and Takhtajan in 86, maybe 80 something. It's a very nice bialgebra. You can upgrade this machinery though. And how do you upgrade it? Well, I want this B to now be rigid. So I'm going to replace it by the smallest braided rigid category. Remember, B just had one generator, so I'm going to add another generator that's going to be its dual. I'm going to add a second generator, let's call it 2, and these morphisms cup and cap, which makes 2 the dual of generator number 1. And I'm going to end up with a smallest braided rigid category, and I'm going to represent that. And this really, for this to be for this object to be a representation of this functor, I'm really imposing an extra condition. I want a dualizable linear YBE solution, and that has something to do with requesting that these two morphisms, let me see if I do this right. These two morphisms, yeah, like this. These guys are invertible. It has something to do with that. If you want more details, I can tell you at the end. But that's the extra assumption that I need on my solutions. Now we have all the background. Yeah, smallest is basically free. Basically free. Yeah, you could, depends what you think of free, but yeah. So the path to enlightenment. What am I doing? So the objects I have in concern are YBE solutions, which go into set. So set theoretical solutions. So my D is going to be the smallest braided category with a very minor condition that actually appears in the set theoretical YBE theory as called non-degeneracy. I can easily restrict, extend to have a functor from B ridge. And so the naive solution, you would say, is, hey, Aryan, why don't you just apply FRT to sets with the Cartesian product? That's a monoidal structure, and it's really, really nice. The problem is, remember, the coend I constructed, I needed it to land in the subcategory of rigid objects. I needed my fiber functor to land in the subcategory of rigid objects, but the only dualizable object with respect to the Cartesian product is the set with one element. There's also another problem here that Hopf algebras in the category of set are exactly groups. And that co-quasi-triangular structure that I was talking about can't actually occur for any group. If you write it down, it has something to do with the fact that the category of G sets can only have a braiding if it's symmetric, if it's trivial, basically. The naive solution to this, so I'm lacking dualizables, let me add dualizables. You can move into rel, which is the category of sets, and where morphisms are now binary relations between two sets, okay? And then every object is its own dual because I have these trivial relations that make every X its own dual. So that problem was fixed, but then another problem occurs that now I don't have enough colimits. I definitely don't have the co-limits I want. So in older papers, what people just do is when they do the theory, they're just like, go to the Yoneda embedding and life is good. But if I want to solve something really combinatorial and set theoretic, if I just jump to the Yoneda embedding, it's like going with a bazooka after an ant. So there's a middle step there that's key, and it's going to be SupLat. The correct solution is embedding everything in SupLat. So my reference for SupLat is going to be Joyal and Tierney's book, which everything I'm going to talk about is in the first like 10 pages of their book. So what is SupLat? It's the category whose objects are partially ordered sets where you have least upper bounds or suprema or joins, whatever you want to call that, for any subsets. And the morphisms are exactly join preserving maps. That's just standard notation. All of these objects are actually going to have meets as well. They're complete lattices because you can always take the join of everything that's a lower bound for your subset. So I'm really talking about the category of complete lattices, but focusing on only join preserving maps instead of join and meet preserving. And the way I'm going to embed set into this is for every set, you can take a power set of it, and that's going to be a complete lattice with the union being the join. In particular, the good thing is that SupLat is complete and co-complete. Unfortunately for us, the co-equalizer structures are horrible, and you really need to think about how to do co-equalizers in this category. The other good thing is that it's a symmetric monoidal closed category. And I'm going to give you the monoidal structure. You take two lattices. You take the product of the underlying sets, you take the power set of this guy, and you impose these relations. And when I mean impose relations, you're taking a co-equalizer in this category of implying that the join inside each of these lattices should become really the join in this power set, which is the union. Having said that, let's move on. What we have is, with respect to this monoidal product, I have that if I tensor the power sets of two things, I'm going to get exactly the power set of their Cartesian product. So I have a faithful monoidal functor. Really, it factors through that rel that I was talking about. And there's this little lemma that if anyone knows a source for it, please tell me. I just proved it, but I'm pretty sure it's folklore, like half of Topos theory. Dualizable objects with respect to this tensor product in SupLat are exactly the free lattices, are exactly stuff of the form, the power set of something. And what happens is really any invertible set theoretical YBE solution or braided object in set is exactly an invertible YBE solution on a dualizable object in SupLat. So this should convince you that this is the perfect case to study these problems. Moreover, the main theorems from the paper that I'm referencing is, so after you get this enlightenment, you sit down and work with Hopf algebras there. And what I saw is that any Hopf algebra you take, you can construct a group, a genuine group in it. So this is some lattice with a bunch of structure maps on it, but you can get a genuine group out of this. And any co-quasi-triangular structure on this guy is going to give you a skew brace structure. Moreover, any skew brace that I was talking about in the first slide can be recovered in this way. It's really the remnant of some co-quasi-triangular Hopf algebra in SupLat. And precisely what I wanted, the remnant of the SupLat FRT, when applied to the power set of a set theoretical solution, is going to give you back, if you apply this construction to it, is going to spit out that universal group. So just one last minute, I'm going to talk about what's the point of doing this. So I said I really want a categorical interpretation to view skew braces as Hopf algebras. And the point is, well, first of all, you can rewrite the theory of skew braces in terms of Hopf algebras. There's 100 years of Hopf algebra theory, and there's 5 years of skew braces. So this should hopefully help you advance stuff. In particular, if you look at the modern theory of skew braces, they tell you this is a set with two group structures, and this is equivalent, to a group with a braiding operator. That really pops up from this Hopf algebraic point of view from transmutation, which appeared in the work of Majid, that any co-quasi-triangular Hopf algebra in any braided category has a second product on it. And that second product in skew braces is really the projection of this larger second product. Moreover, I still need to fill in. So here we have rep theory, and I'm very sure this line here in Bachiller's work is co-representation theory in SupLat, but you're just restricting to some stuff. Other than that, you should be able to apply Hopf algebraic techniques to produce new skew braces, because that's the whole point of the study of skew braces. You want to classify them in order to classify set theoretical solutions, and there's hundreds of Hopf algebraic techniques to produce new ones. And one of the things I've done in the second preprint is just define a notion of Drinfeld twist, which is something for Hopf algebras at the level of skew braces. Something that I'm working on now, which is more fun, is, well, skew braces are examples of something called biquandles, which if maybe you've seen them. You take a knot, you draw the diagram, and you can mark it by a biquandle, and that gives you a combinatorial invariant of your knots. And then we have these quantum knot invariants, which appeared in the 90s from U2G, like the Jones polynomial, where you're looking at the representation theory of some co-quasi-triangular Hopf algebra, and you're applying some TQFT machinery to get some knot invariants. So now I have a theory that says this guy is really the shadow of some co-quasi-triangular Hopf algebra in a suitable category. So what I'm doing now is apply this machinery in SupLat and realize these combinatorial invariants as a shadow of this guy. But there's a lot of subtleties to be worked with. And that's pretty much it. Thank you for your attention. And these are the references, and I've shamelessly advertised the fun article I wrote for Chalk Dust about higher cats and monoidal cats.